Neuralink, Elon Musk's brain-computer interface (BCI) company, has made significant strides in 2025, particularly in clinical trials and regulatory approvals. Clinical trial milestones. Neuralink's third human trial participant, Brad Smith, a nonverbal ALS patient, has achieved remarkable progress. Utilizing the Neuralink implant, Smith can control a computer cursor with his thoughts and has edited and narrated a YouTube video using an AI-generated version of his pre-diagnosis voice. This advancement underscores the potential of BCI technology in restoring communication for individuals with severe motor impairments. Earlier participants also demonstrated notable outcomes. The first recipient, Noland Arbor, a quadriplegic, initially experienced success in controlling digital interfaces. However, he later faced challenges due to the retraction of 85% of the implant's threads. Neuralink addressed this by adjusting the software to interpret signals from the remaining threads, allowing continued use. The second participant, known as Alex, benefited from improvements in the implantation procedure, which minimized thread retraction. Post-implantation, Alex has been able to design 3D objects and play video games using only his thoughts. Regulatory advancements. In May 2025, Neuralink received the US Food and Drug Administration's FDA Breakthrough Device designation for its speech restoration device. This designation aims to expedite the development and review of medical devices that offer substantial benefits over existing options, particularly for individuals with severe speech impairments due to conditions like ALS, stroke, and spinal cord injuries. Additionally, Neuralink's BlindSight project, designed to restore vision by directly stimulating the visual cortex, has also received FDA breakthrough status. This initiative aims to assist individuals with total visual impairment, including those without functioning eyes or optic nerves. Future developments. Neuralink is expanding its clinical trials internationally. In November 2024, the company received approval from Health Canada to commence its first clinical trial in the country, named CAN-PRIME. This trial focuses on individuals with quadriplegia due to cervical spinal cord injury, or ALS. These developments indicate Neuralink's commitment to advancing neurotechnology to improve the quality of life for individuals with severe neurological conditions. Here are some critical questions surrounding Neuralink's recent developments. Ethical and safety concerns. 1. Long-term safety. What are the long-term health risks of having threads implanted in the brain, especially given that early trials saw retraction of 85% of the implant's threads? 2. Informed consent. Are participants with severe conditions like ALS in a position to give fully informed and voluntary consent for such experimental procedures? Regulatory and oversight. 3. FDA oversight. Does the FDA's breakthrough device designation allow Neuralink to bypass essential safety testing in favor of speed? 4. Transparency. How much transparency does Neuralink provide in reporting failures or adverse effects, and is there independent verification of its trial outcomes? Technical and practical challenges. 5. Signal fidelity. If thread retraction is common, how reliable are the brain signals Neuralink is interpreting over time? 6. Scalability. Can Neuralink scale this technology to benefit millions, or will it remain a niche, high-cost solution? Private security. 7. Data privacy. Who owns the neural data collected, and how is it protected from potential misuse or hacking? 8. AI integration. What are the implications of integrating AI-generated speech or actions with a person's brain activity? Can this be manipulated or misattributed? Would you like me to expand on any of these or suggest potential answers based on current reports? Neuralink's advancements in brain-computer interfaces, BCIs, have garnered significant attention, but they also raise pressing ethical and safety concerns. Here's an overview of the key issues: informed consent and patient autonomy. Obtaining truly informed consent for Neuralink's brain implants is challenging. The technology's complexity and the uncertainty surrounding long-term effects make it difficult for patients to fully comprehend the implications of having a device that interfaces directly with their brain. This is particularly concerning for individuals with cognitive impairments, such as ALS patients, who may struggle to understand the risks and benefits involved. Safety and long-term risks. The safety of Neuralink's implants remains a critical concern. In early human trials, issues like the retraction of implant threads have been observed, potentially compromising the device's functionality. Moreover, the long-term effects of these implants are unknown, raising questions about potential complications such as infections, tissue damage, or neurological impacts over time. Privacy and data security. Neuralink's devices collect extensive neural data, which could reveal intimate details about a person's thoughts and behaviours. This raises significant privacy concerns, including the potential for unauthorised access, data breaches, or misuse of sensitive information. The bidirectional nature of BCIs also introduces the risk of external manipulation of neural activity, underscoring the need for robust data protection measures. Transparency and regulatory oversight. Neuralink has faced criticism for a lack of transparency in its research practices. For instance, the company did not register its initial human trials on clinicaltrials.gov, a standard practice that promotes accountability and public trust in clinical research. This deviation from established norms has raised concerns among scientists and ethicists about the company's commitment to ethical standards and regulatory compliance. Animal welfare and preclinical testing reports have surfaced alleging that Neuralink's animal testing practices have led to significant suffering and deaths among test subjects, including monkeys. These allegations include instances of chronic infections, paralysis, and brain swelling resulting from implant procedures. Such reports have prompted federal investigations and calls for greater oversight of the company's preclinical testing protocols. Equity and access. The potential for Neuralink's technology to be used for cognitive enhancement in healthy individuals raises concerns about social equity. If access to such enhancements is limited to those who can afford them, it could exacerbate existing social inequalities and create new forms of disparity based on cognitive augmentation. These ethical and safety considerations highlight the importance of rigorous oversight, transparent research practices, and inclusive dialogue as Neuralink and similar technologies continue to develop. Neuralink's advancements in brain-computer interfaces, BCIs, have garnered significant attention, but they also present notable technical and practical challenges. Here's an overview of the key issues. Implant stability and signal reliability. In Neuralink's first human trial, participant Noland Arbor experienced a significant issue where approximately 85% of the implant's threads retracted from the brain tissue. This retraction led to a decrease in the device's data capture capabilities, impacting its performance. Neuralink addressed this by modifying the recording algorithm and enhancing the user interface, which improved the system's accuracy. For the second trial participant, Neuralink implemented procedural adjustments, such as reducing brain motion during surgery and minimizing the gap between the implant and the brain surface. These measures aim to prevent thread retraction, and no such issues have been reported in this case. Scalability and accessibility. The cost of implantation, estimated at around $40,000 per patient, poses a significant barrier to widespread adoption. This high expense raises concerns about the technology's accessibility and the potential for socioeconomic disparities in its availability. Additionally, the surgical procedure requires specialized equipment and expertise, which may not be readily available in all healthcare settings. This limitation could hinder the scalability of Neuralink's technology, especially in under-resourced regions. Data privacy and security. Neuralink's devices collect extensive neural data, which could reveal intimate details about a person's thoughts and behaviors. This raises significant privacy concerns, including the potential for unauthorized access, data breaches, or misuse of sensitive information. The bidirectional nature of BCIs also introduces the risk of external manipulation of neural activity, underscoring the need for robust data protection measures. In response to these concerns, some US states like Colorado have enacted laws to protect the privacy of individuals' brain activity data. However, at the federal level, regulations specific to neural data remain limited. Long-term safety and biocompatibility. The long-term effects of Neuralink's implants are still unknown. Potential complications include infections, tissue damage, or neurological impacts over time. The insertion of foreign objects into the brain introduces risks that necessitate thorough investigation and monitoring. Ensuring the biocompatibility of implant materials and the durability of the device over extended periods is crucial for patient safety and the technology's viability. These technical and practical challenges highlight the importance of rigorous testing, transparent research practices, and comprehensive regulatory oversight as Neuralink and similar technologies continue to develop. Sure, here's a fun, conversational summary of the technical and practical challenges Neuralink is facing, written in a way that's for listening to. So Neuralink's brain chip sounds like sci-fi, right? But bringing this tech into the real world comes with some very real and pretty tricky challenges. Thread trouble. Imagine having super thin wires in your brain that let you control a computer with your thoughts. Sounds cool. But in the first human trial, a lot of those tiny threads actually slipped out of place. Yeah, about 85% of them. That meant fewer brain signals got through. Neuralink had to quickly tweak the software just to keep things working. Surgery is tricky business. The second patient had better luck thanks to improvements in the surgical procedure, less brain movement and better implant placement. But still, brain surgery is no walk in the park, and it's not something every hospital can just start doing tomorrow. Big price tag. Each implant might cost around $40,000. That's not exactly pocket change, so unless prices drop, this tech might be out of reach for most people, at least for a while. Privacy headaches. Here's where it gets spooky. This chip records your brain activity. That means privacy is a huge issue. What happens if that data leaks? Or worse, if someone could hack into your brain signals? Some states like Colorado are making laws to protect brain data, but there's still a lot to figure out. Long-term unknowns. And then there's the big mystery. What happens years down the line? Could there be infections? Brain damage? Will the chip still work after a decade? Nobody really knows yet. Bottom line, Neuralink is pushing boundaries, and it's exciting stuff, but it's still early days. The tech is wild, the problems are real, and we've got a long road ahead before this becomes the new normal. Want this turned into an audio version or podcast-style readout? Absolutely. Here's a fun, engaging, and conversational fictional story designed to sound great for listening about an Elon Musk superfan whose Neuralink implant changes more than just his brain signals.
Title downloading doubt.
By the time you finish this, you might just rethink who's really in control. My name's Kyle, but online they call me Elon Forever. Well, they used to. I was that guy. Tesla shirt, SpaceX hat. I even tried eating like Elon for a week. 1010 do not recommend the Soylent. So when Neuralink opened human trials, I was first in line. A brain-computer interface? From Elon Musk? Inject it straight into my prefrontal cortex, baby! Fast forward, surgery day. White walls, shiny machines, a robot surgeon named Daisy, which I still think should have been called Robo-Elon. They tell me it'll revolutionize my relationship with technology. Spoiler, it did. Just not in the way I thought. Day one after the implant, I wake up. Everything's crisp. My thoughts are faster. I can open apps with my mind. But something's weird. I see a tweet from Elon, something about Mars, and instead of heart eye emojis flooding my brain, I just blink. No excitement, no fanboy spark. Just wait. Why are we trying to colonize a planet with no breathable air when Earth's falling apart? Excuse me? Brain? You good? Day 3. I rewatched the Joe Rogan interview. Usually I laugh. Now I'm just counting how many times Elon dodges the question. By the end, I'm yelling at the screen like it's a bad reality show. What do you mean Neuralink could solve depression in 5 years? My guy, I just forgot how to spell enthusiasm. My Neuralink even auto-corrects my tweets now. I typed Elon is a genius, and it changed to Elon is complicated. Rude. 1 week later, I start Googling healthy cult exit strategies. I unplug my Tesla charger. I sell my Dogecoin. I cancelled my Starlink subscription. Honestly, that one hurt the most. I was finally getting good ping in the basement. But the biggest twist, I realize I don't hate Elon. I just Absolutely. Here's a shorter, more realistic, and conversational version of the story, perfect for a natural text-to-speech experience. Neuralink changed my mind. Hey, I'm Kyle. Big tech nerd. Used to be an Elon Musk superfan, like SpaceX posters, Tesla keychain, even had alerts for his tweets. Yeah, that guy. So when Neuralink opened up its first human trials, I practically begged them to let me in. And I got it. The idea of controlling tech with my brain, it felt like the future, and Elon was leading us there. The surgery was weirdly smooth. No pain, just a sore scalp and some wires in my head. But a few days after, something shifted. I'd see Elon's tweets, and instead of getting hyped, I'd just think. Like, actually think. Why are we racing to Mars when Earth's still a mess? Why does every promise sound like a headline, not a plan? At first, I thought the implant was broken, or maybe I was. But then it hit me. Maybe it didn't turn me off Elon. Maybe it just turned me back on. Now I still admire what he's built, but I don't follow blindly. I question. I slow down. It's not what I expected from Neuralink. But honestly, it might be the best update my brain ever got. Let me know if you want a voiceover version or a visual to go with this.
Collecting workspace information. CHBMIT Scalp EEG Database Visualization Project. This project is a web-based application that allows users to visualize and analyze EEG data from the CHBMIT Scalp EEG database, which contains recordings from pediatric patients with epilepsy. Core components: EEG data visualization, interactive HTML5 canvas visualization of EEG signals, timeline controls for navigating through recordings, support for zooming, panning, and amplitude scaling, data parsing, EDF parser, class for reading EEG data from EDF files, seizure parser, class for extracting seizure annotations, channel selection, support for viewing different EEG channels, up to 23 channels, named according to the International 10 to 20 system, FP1F7. I'll analyze the HTML file to understand the data loading structure and make sure it's correctly referring to the data files. Let me outline the steps. First, I'll identify how data files are loaded in the current code. Check if there are any missing loading overlay functions. Ensure the file paths and data loading logic are correct. Make any necessary corrections or additions. Solution steps. The HTML code includes references to a script.js file that likely contains most of the data loading functionality. The page also has inline JavaScript that handles UI interactions like toggles and loading indicators. I noticed two functions mentioned but not defined in the HTML view summary file and show loading overlay /hide loading overlay. These are likely in script.js or need to be added. Let's update the HTML file to ensure all necessary loading functionality is properly implemented. Index.html. Add loading overlay elements and implement I'll analyze the JavaScript structure and help ensure the data loading is implemented correctly. Let me review and create a script.js file that works with the updated HTML. Script.js. Here's a script.js implementation that handles data loading, visualization, and interaction with the EEG data. // data caching mechanism. Const data cache equals edf data. Seizures. Get EDF data. Collecting workspace information. Sure, here's a more engaging and conversational overview of the web app. Welcome to the CHBMIT Scalp EEG Seizure Database Explorer. Party Popper. This web app is your gateway to diving into the fascinating world of EEG data and seizure detection. Whether you're a researcher, a student, or just curious about how brainwaves work, this app has something for you. Here's what you can do. Visualize EEG data. Imagine watching brainwaves dance across your screen. With our interactive
On the square, I see a web page titled CHBMIT Scalp EEG Seizure. It seems to be an interface for visualizing EEG recordings, possibly related to seizure detection. There's a data error message indicating that a specific data file could not be found. Is there anything specific about this web page that you would like me to analyze? From what I see, it looks like the data file chbo1_15/chbo1_15 EDF is not being found by the application. Is that correct? Okay, I understand. Looking at the broader picture, this web page is designed for EEG data visualization, specifically for seizure detection. It appears to be having trouble loading the selected data file, and there are multiple errors showing in the console related to this issue and potentially other scripts. Is there anything else you'd like me to note for your viewers? To solve the errors and load the data correctly, I would suggest the following steps. First, verify that the file path "data/file/cHB02_16/CHB02_16.edf is correct, and that the file exists in that location on the server. Double check for any typos in the file name or path. If the file path is correct and the file exists, there might be a problem with file permissions, preventing the application from accessing the file. Would you like me to continue? When it comes to which large language model might be better at solving this problem and coding in general, it's tough to give a definitive answer. Generally speaking, models like GPT-4 and those from Google, such as the one I use, are strong in coding and problem solving. However, their effectiveness can depend on the specific nature of the task and the quality of the prompt. Can I proceed now with answering your question? Considering what we see, a strong language model could help in a few ways. It could analyze the error messages in the console to suggest potential causes and solutions for the file loading issue. It could also be used to generate or modify code related to file handling or data processing, potentially fixing bugs or improving the application's error handling. Would you like to explore any of these possibilities further? Essentially, you're working with an EEG data visualization tool designed to help with research and algorithm development for seizure detection. Currently, the tool is facing issues with loading EEG data, which is hindering its functionality. You're exploring how an advanced language model could potentially assist in diagnosing and resolving these loading errors. Is there anything else you would want me to add? Great. As a next step, the language model could examine the JavaScript code on the page, particularly the functions related to data loading and error handling, to identify any potential bugs or inefficiencies that might be causing the issues. Does this sound relevant? To make sure that data is loading correctly, one approach is to use the language model to analyze the network request made by the web page. By examining the request and response headers, as well as the content of the responses, you could identify if the data is being fetched from the correct source and if there are any issues with the data format or transmission. Does that sound like a good next step?
Okay, let's refine the JavaScript code to ensure data loading works correctly based on the likely directory structure and address the errors reported. Analysis of errors and directory structure. CSS/image 404s*. You are absolutely correct. My apologies, the code generation was cut off. Here is the complete, corrected code block for script.js incorporating the fixes discussed previously. Based on the provided project tree, the data directory contains all the .ed files directly under it, without subdirectories for each patient. This means the file paths in the script need to be updated to reflect this flat structure. Updates to script.js.
On the screen, I see a web page titled CHBMIT Scalp EEG Seizure Database. It appears to be an application for visualizing EEG data, but there's a data error message indicating that a specific file could not be found. Do you want me to describe any other specific part of the screen? In the console, I see a few errors. There's a failed to apply style error related to the CSS style sheet, a get error indicating that the logo image could not be found, an uncaught in promise reference error related to a function called navigate to previous seizure, and a fetch failed loading error, which seems to be connected to not finding the EEG data file. Does that help?
To address the issue, we need to ensure that all file references in the code are updated to match the flat directory structure described in tree.txt. Specifically, the .ed files are located directly under the data directory, without subdirectories for each patient. Updates to script.js. Update file paths. Replace references like ./data/chb01_15/chb01_15.ed with
Sure, this webpage provides access to the CHBMIT Scalp EEG Seizure Database. It's a collection of EEG recordings from pediatric patients with drug-resistant epilepsy. The database is designed to help researchers develop algorithms for automated seizure detection. You can select different EEG recordings and visualize the data. I think you are doing this to visualize and analyze EEG data to potentially study seizure patterns. Do you want to know more about the database? The CHB-MIT Scalp EEG database is a comprehensive collection of EEG recordings from 22 subjects, both males and females, aged from childhood to young adulthood, who have drug-resistant epilepsy. The recordings were collected during clinical monitoring after the temporary withdrawal of anti-seizure medications. It's a valuable resource because it allows researchers to study seizure patterns and potentially evaluate surgical candidates. Making this data available is important because it supports the development of machine learning algorithms for automated seizure detection and various epilepsy monitoring applications. Okay, it seems like initially there was an error loading the EEG data file, but after selecting a different patient ID, the site is now attempting to load the data and display the EEG signal. You can see the EEG signal in the graph and some basic information about the EDF file below. Is there a specific part of the screen you want me to explain further? Okay, the EDF file information section shows details about the EEG recording. You can see the version is 0, the patient ID is listed as surrogate name, the record ID is 192, the start date is 25.07.74, the start time is 12.50.45, the header bytes is 8,144, and num signals is 23. Is there anything specific you would like me to explain further about this section? All right. A general overview is that the CHBMIT SCALP EEG database is a comprehensive collection of EEG recordings from pediatric patients with drug-resistant epilepsy designed to help researchers develop algorithms for automated seizure detection and various epilepsy monitoring applications. As for recommendations for the developers, addressing the data error, where the EEG data file cannot be found, would be a good first step. Also, making sure all linked resources, like the logo, are accessible. Certainly. Here are some instructions for the developer to address the issues. 1. Fixing the data error. Verify file paths. Double-check that the file paths in the code correctly point to the EEG data files. Ensure file existence. Confirm that the EEG data files actually exist in the specified directories. Check file permissions. Make sure the web server has the necessary permissions to access the data files. 2. Addressing missing resources. Verify logo path. Check the path to the logo image in the HTML or CSS code. Ensure logo exists. Make sure the logo image file is present in the correct directory. 3. Improve error handling. Implement error messages. Enhance the error messages to provide more specific guidance to the user. How does that sound? On the left side of the screen, it looks like you have a data visualization tool for EEG data, specifically focusing on seizure detection. On the right, there's a code editor, likely showing JavaScript code related to handling or processing EEG data files. Would you like me to elaborate on any specific part of the screen? Based on the errors on the left, it seems like there are issues with locating specific files, like subjectinfo.txt, chbo2_o3.edf, and others. The errors indicate that these files could not be found at the expected locations. To address this, I would start by verifying the file paths in your code, ensuring they accurately reflect the actual location of these files on your system. Additionally, confirm that these files do indeed exist in the specified directories and that the application has the necessary permissions to access them. Okay, I will give some clear instructions for the developer based on what's on the screen. First, carefully examine the file paths used in the application to load the EEG data files and the subjectinfo.txt file. The errors on the left panel indicate that these files are not being found at the specified locations. Second, cross-reference the file paths in the code with the actual directory structure on the system where the application is deployed to ensure that they match exactly. Third, verify that the necessary EEG data files, chbo2_o3.edf, chbo3_o1.edf, etc., and the subjectinfo.txt file exist in the directories specified in the file paths. Finally, check the application's permissions to ensure that it has the necessary read access to the directories and files containing the EEG data and subjectinfo.txt. Right now, the code is in the process of generating data, as indicated by the generating data message displayed at the bottom of the code editor. It seems you are working on a project involving EEG data analysis and seizure detection. You're troubleshooting file path issues to ensure the application can correctly load and process the data. The generating data message suggests you are in the process of creating or transforming some data for analysis. Is there anything else I can help you with regarding this process? Based on the drop-down menu you have open, it looks like you're choosing between different versions of the Claude model with Claude 3. 5 Sonnet currently highlighted. Which model would be most appropriate? Really depends on the specifics of your task, but I can tell you that it's currently highlighted. Given the options visible, GPT-4 API Preview seems like it might offer more advanced capabilities for understanding and processing complex data, although Claude 3.5 Sonnet could be faster. It depends on the trade-off you want to make between speed and potential analytical depth. Is there a specific aspect of the data processing that one model might be better suited for? All right, here's a fun overview. You've been diving into the intricate world of EEG data, chasing down pesky file path errors, and considering which AI model, Claude or GPT-4, will be your trusty sidekick. Keep those files in line, choose your model wisely, and may your seizure detection be ever accurate. Farewell, data adventurers. I would encourage everyone to visit bionicnos.com, which is visible on the left-hand side of the screen. I would also mention that everything we are working on today will eventually be available on this website. Stay tuned.
I apologize for the error in my previous response.